In the last example, we gave a geometric argument involving an improper integral to show that the sum, n goes from 1 to infinity of 1 over n squared, is convergent. And we kind of just made, like I said, a geometric argument to bound the area. So we thought of it as areas, and we bounded this by areas. So let's think about now a different sum. So the series n goes from 1 to infinity of 1 over the square root of n. And let's try to make a similar argument. But this time we're going to guess, maybe, so as n gets really big, n squared gets bigger very fast, right? Square root of n does not get big quite as fast. And in the last section of the notes, we proved that the sum as n goes from 1 to infinity of 1 over n is divergent, right? So this is called the harmonic series, and the harmonic series diverges. And we would assume that as n gets big, the square root of n is going to be smaller than n, and therefore 1 over the square root is not going to shrink down as quickly as even 1 over n, which is divergent. So what we would like to do then is try to make a geometric argument to show that this series is divergent. But let's do it by an argument that's similar to the one that we made for 1 over n squared. So here's what we did. We said, okay, let's replace our series by a function, and I've drawn this not very smooth, but this is supposed to be the function f of x equals 1 over square root x. Okay, and remember that the series is then, the terms of the series are given by picking out just the integer values in the domain down below, and then going up to the curve up above. And in the last example, so for 1 over n squared, we drew some boxes to represent the area, to represent the series as a sum of areas. In this example, what I want to do is draw the boxes still, but draw them so that the terms of the series, of the sequence of the series, so that those are the left end points of the boxes. So these boxes are all a little bit bigger than the curve itself, right? And so the idea is now the series is equal to values of the series. The sum is equal to the sum of the areas of these boxes. And just like we did before, we can kind of see, okay, well, each of these rectangles is slightly larger than the curve itself. And so whatever our series is, its value has to be bigger than the area underneath the curve. And the area underneath this curve is, of course, given by an improper integral, which we can compute. So this is the improper integral right here. And just as we did before, we can say, okay, well, our sum, n is equal to 1 to infinity, 1 over square root n. This series now must be greater than or equal to. So now we're switching the perspective here. Like I said, in the last example, we bounded the series in the other direction. But this should be greater than or equal to. It has to be greater than or equal to the integral from 1 to infinity of 1 over square root x dx. Okay? And this is something that we can compute. So let's do it. Well, as we know, improper integrals have to always be treated properly, right? And so this could be converted to the limit, the upper limit of infinity is converted to a limit down below, limit as t approaches infinity, of integral from 1 to t, and I'm going to rewrite this as x to the negative 1/2 power. Okay? And then this integral, of course, is, well, maybe that's not even, maybe I shouldn't even be writing it like this, because if I just do this, then it's obvious what the antiderivative is, right? Antiderivative is then 2 square roots of x. So this becomes the limit as t approaches infinity, 2 square roots of x from 1 to t. And then if we plug in, this is the limit, t approaches infinity, 2 square roots of t minus 2. All right? And as t gets larger and larger and larger, the square root itself blows up, right? And we end up with plus infinity. So the improper integral itself is divergent. But look what we've got now. This integral is positive infinity, and the series, the value of the sum of the areas of the rectangles is larger than the area underneath the curve. And so just by a geometric argument alone, that must be positive infinity itself, right? Or even bigger than this, at least this magnitude of positive infinity. And so our conclusion then is that this sum must diverge. So the sum 1 to infinity, 1 over square root n, has to be divergent. Okay? And so in these last two videos, if you take these two videos together, in the first video, so that was the sum of 1 over n squared. I think I still have the picture here. In this video, we bounded the areas below. They were below the curve, right? And we were able to add up we were able to think of the series as a sum of areas that are all below the improper integral. They're bounded above by the improper integral, and this improper integral converged. Okay, the improper integral converged, and so that meant that the series converged. Now in this example, we drew our rectangles so that they were larger than the curve. They're always outside of the curve, and the curve itself was divergent, so the series is larger than the integral, and the integral diverged, and therefore the series diverged. Okay, and these two comparisons are very useful, but they both take into account that the function, in both cases, the function is positive and decreasing. It's always above the x-axis. We're never going below the x-axis. And not only that, but even though this one is decreasing very slowly, it takes a long time to decrease, the function is always squeezing down toward the x-axis, and it's decreasing as x goes out to infinity. Okay, and so we'll make this idea more formal in the notes after this video, but this is all related to a test for convergence called the integral test.